Welcome students, welcome to the series of lectures on continuous probability distribution. Actually, this is a series of lectures on statistics, and in that we are into probability distributions. We completed discrete probability distribution, entering into the continuous probability distribution, and even in the continuous probability distribution we covered normal distribution, t-distribution, and this session is about chi-square distribution. Okay, if you have watched the session of normal distribution and t-distribution, then what was the extreme value of normal distribution and t-distribution? As in, what is the tail end of normal distribution? As in left tail and right tail. It is minus infinity till positive infinity. It is minus infinity plus positive infinity. Right, both in normal distribution and t-distribution. So if you are choosing any data point that you're forcing to be normally distributed or t-distributed, then you have to test whether that data point goes from minus infinity to positive infinity or not. Even the probability is bleak or not. But the problem is we know there are a lot of entity which does not go below zero. For example, stock prices, bond prices, variance. Have you ever observed or seen any stock price that go below zero, which has a negative value? It doesn't. You are saying in normal distribution and t-distribution that the value can go up to minus infinity. Yes, definitely the probability is bleak, but it can go up to minus infinity or even negative value like minus 1 or negative 0.01. But stock price, bond price will never fall below zero. Whatever distribution it follows, doesn't matter. The value of stock prices, the bond prices are pegged at zero. So how we can force any stock price on this planet to be normally distributed or t-distributed? We shouldn't. Similarly, variance. Why variance? Because what is the formula of variance? It is a summation of x minus mu whole square upon n. It is a square value and then you're doing the summation. How the variance value, any variance value will go to negative values or go below zero? It's not possible. So we need a distribution. We need a distribution which is pegged at zero, and definitely it can move up to infinity. Yes, stock prices can move up to infinity. There is a possibility. The probability is very low, doesn't matter, but it can. Any day, there is no limit to the stock prices, right? So, yes, we need distribution which are what? Right skewed distribution. What distribution? A right skewed distribution. But there are different right skewed distribution. There are different right skewed distribution. There's one F distribution, which is a right skewed distribution. There is a chi-square distribution, which is a right skewed distribution. There is a log normal distribution, which is a right skewed distribution. So the question is, which distribution to use when? And actually, we are discussing what? We are discussing chi-square distribution. So my question is, when we can use chi-square distribution? Whenever we feel like? The answer is no. We can only use chi-square distribution when this condition gets satisfied. What? This condition gets satisfied. What is the condition? It should be standard normal data. Then you do the sum of square of that data. That will become chi-square distributed. Mathematically, you write it down like this. Any entity is chi-square distributed if you are taking the sum of square of standard normal variable. What standard normal variable? I think till sum of square it is clear. But what is this standard normal variable? What is this standard normal data? So you see the notation of z, where you have seen the notation of z earlier in normal distribution. Z was what? Z score, which was x minus mu x minus mu upon sigma. What it was? It was distance from the mean in the terms of standard deviation. It was distance from the mean in the terms of standard deviation. So those z value, if you take the square of those z value and sum it up, it will follow chi-square distribution. Let's deep dive into z value or standard normal data. Now assume you have a data which is normally distributed with a mean of 2 and the standard deviation of 3. So this point is 2, this point is 5, this point is 8, this point is -1, this point is -4. If I say how many standard deviation 2 is away from the mean, you will say what? X minus mu upon sigma, 2 minus mu upon sigma, that is 2 minus 2 upon 3, that is 0. If I ask you 5 is how many standard deviation away from the mean, then you will do 5 minus 2 upon 3, that will be 1. If I say how many standard deviation 8 is away from the mean, you will do 8 minus 2 upon 3, that will be 2. If I ask you how many standard deviation -1 is from the mean, you will do -1 minus 2 upon 3, that is -1. Similarly, you will do -2. Right. So you see that the standard normal data, which is the z-score, has a mean of 0 and the standard deviation of 1. So any data which is normally distributed has a mean of 0 and a standard deviation of 1 is called as standard normal data. And z-score is one of the standard normal data. There could be any entity in the world which is normally distributed with a mean of 0 and standard deviation of 1. But definitely z-score is one of the entity. Okay. So what is the general definition of standard normal data, or what is the universal definition of standard normal data? That it has a mean of 0 and a standard deviation of 1 and it is normally distributed. If you take those data, do the square of that and do the sum of that, that will be chi-square distributed. Now tell me which entity in all these three you feel is chi-square distributed. Is it stock price? Is it bond price, or is it variance? The answer is variance. Why? See, what is the formula of variance? The formula of variance is summation of xi minus mu whole square upon n. If you expand it, the formula is x1 minus mu whole square upon n plus x2 minus mu whole square upon n plus x3 minus mu whole square upon n, and so and so forth till xn minus mu whole square upon n. Now, if this x, all the x is normally distributed, what are you doing? You're doing x minus mu, and now what I'm saying, divided by a constant, and that constant value is the variance value of this data. So what will happen? It will have sigma square, it will have sigma square, it will have sigma square, it will have sigma square. If you see this section, this is what? Z value. If you see this section, what is this? Z value. If you see this section, it is Z value. So intuitively, this is not the correct manipulation to prove whether the variance will approach chi-square distribution or not. That manipulation or that description is quite complex. But you can see that intuitively, variance will start following chi-square distribution. So, very important point. When you study hypothesis testing, if you have to test mean, you will use normal distribution or t distribution. But if you have to test any hypothesis about variance, you will only use chi-square distribution. You will only use chi-square distribution. If it doesn't say the ratio of variance, it only says variance or standard deviation, you will use chi-square distribution. Okay. So yes, variance also start following chi-square distribution. So this was the introduction of chi-square distribution, right? In the next lecture, we'll try to understand with the help of Excel that how the sum of square of standard normal data, the sum of square of standard normal data start following chi-square distribution. We'll also try to understand what is the concept of degree of freedom. What is the concept of degree of freedom? Is it the same degree of freedom that we studied in normal distribution and t distribution, or in the formula of variance? So we'll understand the degree of freedom, and we'll also try to understand that how and why chi-square distribution is also a family of distribution. And the last thing that we'll understand in the next session is that how to read and understand chi-square table to do prediction and solve hypothesis question. So with that, we'll pause here. Thank you. Have a nice day.